This is Raghupati. Let us see unit number 2 in this strength of materials 1 subject. So what are the topics to be covered in this unit number 2? Here the first one is the types of load supports beams, the concept of shearing force and bending moment, SFD and BMD for cantilever beams. So these are all some topics to be covered in the unit number 2. So first let us see what is beams. The topic of the unit number 2 is stresses on beams. What are the types of stresses acting on the beams? So that thing we are going to see in this unit number 2. So first let us see some of the introduction of beams. Beam is a horizontal member which is carrying transverse loads and subjected by internal forces such as shear forces and bending moments. We have seen some other kind of stresses in the unit number 1. That was axial compressive stresses, axial tensile stresses, shear stresses. Like that we have seen different types of stresses. If we take any material or any member, when it is subjected by axial tensile force, then that member is subjected by only the axial tensile stress. Like that, any member which is subjected by axial compressive force, then that member is subjected by axial compressive. But in this beam, we have applied some transverse load. Transverse loads means the load which is acting perpendicular to its length axis. Okay, that is called as transverse loads. So in that beam, it is subjected by different types of loads. Then the internal forces are developed. So that forces are nothing but bending moment and shear force. So any horizontal member which is subjected by transverse load, then it is having some internal forces such as shear force and bending moment. So that member is called as beam. Beams are used in buildings and bridges to support these slabs. So beams are nothing but supporting members. Okay. Usually beams are supported on column or wall supports. These beams are supported in walls or sometimes at columns. And sometimes it is supported over another beam. You see that this is a main girder or main beam which is supported by this end column here, one. The another column may be at that side. Okay. So the beams may be supported over columns, or sometimes it is supported over walls, or sometimes. So you just see here one more beam is coming where it is supported at this beam. So like that a beam is supported over another beam. The distance between the support is called the span of beam. Like that. So here a column, let us assume here a column is presenting, and therefore the distance between these two supports are called as span of beam. Loads on beams. Beams are carrying transverse loads, that is perpendicular to the beam axis and the transfer to the beam support. This is the beam axis. We can represent the beam by just draw a line. This is nothing but beam. It has two supports like this, and these loads which are acting perpendicular to the axis of beam, length axis of the beam. So these are called as transverse load. In buildings, load can come from the self-weight of beams, weight of slab, floors resting on beams, loads due to furniture, equipment, then people resting on the floors, loads due to wind, horizontal forces, or earthquake, etc. So these are all some type of forces or acting on the beams. Okay. Physically, these all loads are being transferred into beams from slabs, or it may be directly acting on beams. Let us see some type of forces acting on beams. Just let us take first concentrated forces. The concentrated forces means a force which is acting on a single point, or it is concentrating on a single point on the length of beam. Like that you see that here W1 is acting at some point, like that W2 is acting at some point. So it can be referred from either left support or right support, whatever may be. So I can refer this W1 like it is a distance of small length from left support, like 2 meter from left support. Like that we can also refer from right support. It may be this W1 is acting at a distance of 3 meter from right support, like that we can refer. Okay, so a concentrated force is which acting at a point, single point, that is called as concentrated force. Next, let us see the uniformly distributed load. So this is nothing but whatever the load that we are distributing evenly into throughout the length of the beam. So at any point it is subjecting a constant force. So that is uniformly distributed load. Sometimes if we have a single point load at center, so this single concentrated force can evenly be distributed throughout its length. So that is nothing but UDL, or this UDL load can also be placed or assumed at a concentrated force at this location, or at centroid of that span of beam, or centroid of that span of load. Suppose here this beam, the span of this beam may be, let us take as 3 meter, then it is subjecting a 10 kilonewton per meter. Thus this load should be represented like that, W per unit length, like that 10 kilonewton per meter. The total span of the beam is 3, and therefore the total load is 30 meter. 3 into 10 kilonewton per meter. So therefore the total load acting on this beam is 30 kilonewton. This 30 kilonewton can be assumed to place over at centroid of this span of this load, like that we can assume. Then the another load is uniformly varying load, which is nothing but the load starts at a 0 at one end and ends at a maximum magnitude at another end. So this is called as uniformly varying load or linearly varying load. And this is, you see that another type of load we can apply directly as couple into beam, as couple or moment into beam at a single point. And also this couple can be represented like this. Okay. So these are all the different types of loads acting on beams. Next, let us see the types of supports. What are the types of supports on these beams? Beams are in practice supported on walls, other beams, columns, piers or abutments. Yes, these supports are always producing opposite and equal magnitude of reaction forces acting on the structures. The reactions are normally assumed to be concentrated. You see that whatever the loads acting on beam, so this load is finally being transferred into its supports. Okay, its support. That supports may be of columns, piers or abutments, or sometimes walls or other beams. Okay, so whatever the loads distributed into this beam, finally it is being transferred into its supports. So that support is nothing but producing equal and opposite force. Suppose if there are two supports, in this case if there are two supports, so whatever the loads are acting on the beams, it was shared into these two supports. Okay, it is shared into these two supports. So that is happened. So there are, let us see some types of supports. First one is the roller support. So let us see this one. It is set as roller support. It arrests only, so then these are all some of the properties of this roller support. The roller support arrests only the vertical displacement. It allows horizontal displacement and rotation. This support offers vertical reaction only. So let us assume, suppose if we have a suitcase and which is fitted by a roller at its base. So if you kick or push the suitcase along horizontally, what happens? Simply it moves because it is fitted with the roller at its base, and therefore whatever the force we give along its lateral direction, it moves, simply it moves, which means there is no resistance offered along the horizontal direction, because it is having the rollers, frictionless roller, and therefore it moves laterally or horizontally. So it doesn't offer any horizontal resistance. So that so it allows horizontal displacement and rotation. Okay, and it also allows rotation. Rotation means whatever the force it is given into this beam, the beam is tending to bend or deflect. So at support the deflection may becomes zero, because the supports offers vertical reaction, and therefore it won't allow any deflection at the support, but it allows rotation, which means it may bend. Okay, at the supports, over the support the beam may bend small, it allows rotation. Okay, then next we have hinge or pinned or simply support. So this is the another type of support. You see that it can be represented like this. So the difference between this roller and hinge means it doesn't have any roller over it, that's all. And therefore if there is no frictionless roller fitted in this support or in this member on this beam, and therefore now if we give any force, either lateral or vertical, it won't move, it does not move, because it is having a resistance. Suppose I give a vertical force in this over this support, it doesn't move, the support does not allow any deflection. Like that, if I give lateral force, it doesn't move, because the support is giving a lateral resistance, and it is offered a lateral resistance. There is no horizontal displacement at this support, so it allows rotation only, and therefore the support allows only rotation. Okay, this support offers vertical and horizontal reactions. So both vertical, because it doesn't allow any the vertical displacement as well as the horizontal displacement, and therefore it is offering the vertical and horizontal reactions both. Next we see the fixed support. This is another type of support. It arrests both vertical and horizontal displacement. It also arrests rotation. It doesn't allow any rotation. Okay, there is no rotation taking place. So this support offers vertical and horizontal reaction, and also it is having the moment reactions. Okay, so at this support it is subjected by some moment, because it doesn't allow any rotation, and therefore it is offering the equal and the opposite nature of force, a moment force. Okay. So these all are the different types of supports which introduced into the beams. Next, so these are all some of the terminologies in beams. You see that, so this beam, as we have already discussed about, so these two are supports. These supports are normally represented as the upper arrow at its ends, and the distance between these two supports are called as clear span, and the center to center distance between these supports are called as effective span. Okay. So symbolically, a simply supported beam is represented by a horizontal line with loads on top, at least two upward arrows representing support reactions. Okay, so like that we can represent, and these are all the different types of load. This one may be of UDL, uniformly distributed. These two are concentrated forces. Next, let us see the types of beams. The first one is simply supported beam. Then second one is cantilever beam. Third one is overhanging beam. Fourth one is fixed beam, and fifth one is continuous beam. You see that first one is the simply supported beam. So which means the simply supported beam is having two support at its ends. And we know these two supports are called as hinged support, and we know the properties of this hinged supports. Suppose if we take this beam, it is subjecting only the vertical forces, and therefore these two supports are having vertical reactions at its ends. Okay, vertical reactions, and this at its two ends it is not subjecting any deflection, but it is allowing the rotation. So this is the properties of hinged supports. Okay, it allows the rotation. So this beam may bend like this. This beam may bend like this. Yes. Next, cantilever beam. Cantilever beam is said as there is a support called as fixed support at its one end, and the another end it is being free. It is being free means it is not supported using any supports. It is simply free, whereas the one end it is fixed. It is fixed with some wall or some other supports, so it may be fixed. So this is called as fixed support. Yes, we know the properties of this fixed support. It is having vertical and horizontal reactions, as well as it is having the moment reaction, because it doesn't allow any rotation. Like that, it doesn't allow vertical deformation and horizontal deformation. So as far as this case is concerned, this beam is subjecting only the vertical forces, and therefore it is providing it is producing only the horizontal reaction. Suppose if this beam is carrying any horizontal forces, then it is producing the horizontal reactions at its ends. Okay, so whatever the forces are acting on this beam, the whole reactions are produced by only this fixed support, because in the other end it doesn't have any supports. That is called as cantilever beam. So cantilever beam can simply be said as it is a horizontal member at its one end fixed and the another end is free. That is called as cantilever beam. Like that, the another next type of beam is overhanging beam. Overhanging beam means it is nothing but just a simply supported, but at its ends it is having at its end the member is projected. That is at its ends it is having a free end, and the another end is supported at this hinged support, like that here. So the overhanging beam may be extended over this entire supports, that is two supports, or it may be extended at any one of the support. So like that, the overhanging beam is so this beam, in this beam you see that it is subjected by the vertical forces, and therefore these forces are shared by these two supports. Okay, these two supports at its end, at its ends there is no support. It is freely hanging. And we know that since it is a hinged support, it is having rotation at its end. Okay, it is having rotation at its ends, but it doesn't allow any deflection. So you can say a overhanging is a beam which is supported at its two ends by simply supports or hinged supports, and at two ends simply the beam or the beams are projected or extended at some length. Okay, so it may be extended beyond at its two supports or at any one support. Okay. Next, we just see the fixed beam. Fixed beam means in cantilever case there is only one support, fixed support at its one end, whereas the another end is free. But in case of fixed beam, it has two fixed support at its two ends. That is called as fixed beam. Okay, you see that this is a typical diagram of fixed beam. It is a typical diagram of fixed beam. It has fixed support at its two ends, this one end and this another end. Now it is subjecting the transverse loads. Okay, so now these two supports are having the vertical reaction, it is upward vertical reaction, horizontal reaction, as well as the moment, reactive moments, like that. This support is also having the vertical reaction, horizontal reaction, as well as the moment, reactive moments. So like that, it is having totally 6 reaction components. In this case, it is carrying only the vertical forces, and therefore we simply neglect the horizontal reactions for this case, because it doesn't produce any horizontal reaction, because this beam carry only the vertical forces. This beam carries only the vertical forces, and therefore there is nothing horizontal components produced. Okay, and therefore as far as this fixed beam is concerned, it is having totally 4 reaction component. 2 is the vertical reactions, and 2 is the moment reactive forces. Totally 4 reactive components, whereas this beam, simply supported beam, is having only 2 reaction components, that is VA, vertical reactions at A, support A, let this one be the support B, and therefore it is producing the vertical reaction component VB. And this cantilever beam is having 2 reaction components. One is vertical reactions VA and the moment reactions MA. We don't bother about the horizontal reactions, because this beam is carrying only the vertical forces. Like that, this overhanging beam, it is having the only 2 reaction components. One is this support VA and another one is this support B. But in this fixed support, it is having 4 reactive components, VA and MA, then VB and MP. The next, let us say the continuous beam. Continuous beam means a beam which is continuously running. It is having spans of more than 1. You see that this is one span, and this is another span, this is another span. So there are 3 beams combinedly said to be a continuous beam. You see that this is one of the end support, and these 2 are called as end supports, and these 2 are called as intermediate supports. Like that, we can further continuing the beam by introducing the intermediate supports and ending with another support. So this end supports may be simply support or fixed support, or it may be freely overhanging sometimes. Okay, but all the intermediate supports are representing like this arrow. Okay, so this is called as continuous beam. So a continuous beam may have any number of spans. So in this case, we have only 3 spans of continuous beams. So sometimes we can use the continuous beam as 4 spans, 5 spans, 6 spans, etc., etc. Like that, it can be extended. So that is called as continuous beam. Next, let us see the bending moment. What is bending moment? So bending moment is nothing but the internal force acting on this beam. Bending moment is nothing but an internal force acting on the beam. Okay, so that is internal forces means resistance offered by the beam due to transverse load. That is called as bending moment. You see that the bending moment can be calculated by make the algebraic sum of moments. So the moment is nothing but force into perpendicular distance, either left or right of the section, is called as bending moment. You see that if we take any beam, suppose this one a beam of span L, okay, this one be a beam of span L. So throughout this section, this beam may be subjected by different magnitude of bending moment. Suppose I want to know the bending moment at this point or this section, so in which I can calculate by make an algebraic sum of moments either left or right of this section. So the moment can be calculated with respect to any section. Suppose here I want to know the bending moment, so I just make the algebraic sum either left side of the moments. So this one will be the left side. So I just make the algebraic sum of left side moments with respect to this section, or I just make the algebraic sum right side of this section. So we just make the algebraic sum of moments either left or right of this section. So that one is called as bending moment. So bending moment is nothing but an internal force offered on this beam due to external transverse forces. This bending moment is calculated by means of making the algebraic sum. Suppose this bending moment should be calculated at any section, because every section is having different magnitude of bending moment. Okay. So like that, the bending profile of the beam due to bending moment can be either sagging or hogging nature. You see that when the transverse force acting on this beam, either it may be of UDL or concentrated force. So because of that force, what happened? The bending moment is subjected. Because of this bending moment, the beam is tending to bend. The beam is tending to bend. So that nature of bending profile may be either it may be of sagging or it may be of hogging, like that. It is having two kinds of bending profile. Okay, here the positive sign is assigned for sagging bending moment. So because in order to find out the bending moment, so we have to make the algebraic sum. Algebraic sum means we must make the sum of moments with the sign convention. So with the sign, either it should be positive or negative. We must consider the effect of sign in this case, and therefore, so at any section, when we make the sum, when we make the all sagging nature of bending effect of moments, then we just put the sign positive, like that. The bending moment calculated by upward for sagging bending moment, and the negative sign is assigned for hogging bending moment. So, then if we have the bending profile like this hogging, in that case, what happened? This bending, we just put the sign minus. So with respect to any section, we just make the algebraic sum of moments. So that moments may be of either sagging or hogging. In case of sagging, we put the sign positive. In case of hogging, we put the sign negative. Next, we just see what are all the sagging moments and what are all the hogging moments. Normally, the bending moment calculated by upward forces or reaction forces. Suppose the beams are carrying only the downward forces, then reactions are produced upward directions. Am I correct? Because the nature of reaction is producing equal and opposite nature of forces. Am I correct? And therefore, if the beams are carrying vertical downloads and the reactions are producing in the upward forces. Now, suppose the moment is calculated by means of these upward reaction forces into some distance. Suppose I want to know the bending moment at this section, and therefore if there is a reaction forces at this end, this is upward force. This upward force into this distance, I want to know this bending moment at this section. This force into distance, which produce the sagging moment, that is called as reaction forces, which induce the sagging bending moment along the span of the beam. Like that, the bending moment calculated by downward forces. Like that, suppose I choose this section here to find the bending moment. In between this end of the support and this section, when it carries some downward forces, so I can also include the moments due to these downward forces. These downward force into distance to calculate the bending moment at this section. Therefore, this downward force into distance which produces the hogging moment, and therefore I put the sign minus. So, in order to calculate the bending moment at this section, first the moment produces due to reaction force, that is called as sagging, and the moment produces due to the applied downward forces, that is called as hogging moment. A combination of these two, the net bending moment at this section can be calculated. So like that, we just find the bending moment at every section of the beam. So this is the sign convention that we follow for in the calculation of the bending moment. So therefore, net bending moment along this span is obtained by the difference of sagging and hogging moment. Then the fixed support moment is the algebraic sum of moments along the span, but in opposite nature, since the support is producing reactive force. There is one more bending moment at fixed support, which is called as the reactive moments. That thing we have already discussed, which is nothing but we just make the sum of all span moments. Span moments is only due to the downward force, applied forces, and its opposite nature of couples or direction that we simply introduce in that fixed support. Suppose the fixed support is introduced at the right side, and the span moments are in force into distance with respect to this support. It is producing anti-clockwise direction moments. Therefore, sum of these anti-clockwise moments what comes. So we simply put the opposite nature of clockwise moment at this, whatever the magnitude that we obtain, the sum of all anti-clockwise moments with respect to the support, and the same moment is being acted at this fixed support in opposite nature. It may be of clockwise. Like that, if a fixed support is at left support, then the span moments due to these downward forces all are in clockwise moments, and therefore the reactive moment is at this fixed support is anti-clockwise in nature, which is equal to this all span moments. So like that we can find the fixed support moment in case of cantilever beam. So next let us see this shear force. Shear force is nothing but the moments, shear force in this beam is acting due to the difference in moment. Suppose you see that if we have a beam which is m at this point, whereas some distance dx, and there will be moment m plus dm, because the moment are not constant throughout this section, and there will be a difference in moments at a point to point, and therefore there will be a difference in moment, and therefore one end it is having m, the another end it is having m plus dm. Okay, so that one is said as here the moments m and m plus dm are obviously not in equilibrium. There is a net moment dm, it may be in anti-clockwise direction. This would be balanced by shear forces F on either side of the beam of length dx. So this dm can be balanced by the shear on either side of the beam of length dx. So for moment equilibrium, sigma m equal to 0 is equal to dm minus f into dx, which should be equal to 0, or dm is equal to f into dx, therefore f is equal to dm by dx. Like that we can find the shear. The difference of moments at different locations with respect to distance are called as shear force. So the shear force can also be calculated the algebraic sum of vertical forces on either left or right side of the section is called as shear force. So here it is assumed a cantilever beam which has 6 segments A, B, C, D, E and F. Let us assume a cantilever beam which is being assumed as a 6 segments A, B, C, D, E, F, and at its end of A it is subjected by a force W. So actually there are infinite segments. Here for explanation purpose we just split into 6 segments, but we can split this beam into infinite segments by having different slices of this beam. Okay, here F gets an upward force on wall and downwards force from E. You see that F gets an upward force on wall. So because here the wall is a fixed support which produce equal and opposite nature of reactive forces, and therefore at wall, as far as this F is concerned, the reactive forces, it is having an reactive forces W an upward direction, but from E it is having a downward force. You see that the load W is transmitted by segment F to the wall as W, that is downward force, but F gets an upward force on the wall, that is reactive forces, and a downward force from E. From E it is having a downward force. So in order to balance or equilibrium in order to maintain the equilibrium, it is having an upward force, and from E it is having a downward force. Like that, segment A gets the downward force. Okay, segment A gets the downward external force and gets an upward reaction from B. Okay, from B it is having an upward reaction from B. So like that it is sharing to maintain the equilibrium. This is called as a positive shear force. So what we have, suppose we have the segment like this. Suppose we have a segment like this, and its left side portion it is having an upward shear force, and right side direction it is having a downward shear force, that is equal shear force. So like that we have the two shear force at its two ends in order to maintain this equilibrium. So this kind of shear force acting on the segment or section is called as positive shear force. This is called as positive shear force. Like that, when it is having a tendency of opposite in nature, these two shear forces, when the left side it is having a downward shear force and right side it is having an upward shear force, then it is called as negative sign. It is having the negative sign approach. Okay, so like that, a shear which acts towards upward direction on its left side and a downward direction on its right side, then it is subjected by positive shear. Any section, suppose if we have this section, if we take this section and this one be the left side and this one be the right side, so left up means it is positive, right down means positive, whereas left down means negative, right up means positive. Like that we use the sign convention to find the algebraic sum of vertical forces or at any particular section in order to calculate the shear force. So far we have discussed the sign convention used for shear force. Finally we conclude that the left portion of upward direction of shear force is positive shear, and the right side, the downward nature of shear force, is having positive sign. Like that, in the left side portion, when the shear is acting towards downward direction, it is negative. Right, that right side, the tendency of shear force is upward, then it is negative sign. So like that we are using the sign convention for shear force. Simply left up, right down are positive, left down and right up are negative. Like that we can use the sign convention for calculating the shear force. So you see that a shear force shall have two equal and opposite forces and not just one force. In a beam segment carrying distributed external load, the force on either side would be different and the shear force would vary. You see that in a beam segment carrying distributed external load, the force on either side would be different and the shear force would vary. So in this case, if we have a uniformly distributed force, now you see that the shear is not constant. Here F plus dF is acting, here F. We have F plus dF, here F, because the force is varying, uniformly varying, and therefore at this point it is having only F, whereas here F plus dF. So there is a difference in shear. So dF is equal to is nothing but this W into dx. Okay, dF is equal to this W into dx, therefore this W is equal to dF by dx, and therefore F is equal to integration of W into dx. Like that we can represent the shear force F, and thus dm by dx is equal to F or integration of W into dx. Like that we can find. So dm by dx equal to F, that thing we have seen in the previous slides. Here we just see the F is equal to integration of W into dx, or W is equal to dF by dx. Like that we can write the expression. Next, let us see how can we draw the shear force diagram. The shear force on every section on this cantilever beam is same. in this case it is having a fixed support. Since it is a cantilever beam, it has fixed support at its one end and free at the other end. Here a force W is acting sorry here a force W is acting at its right end, that is at its free end, and therefore we have an equal and opposite nature of force, that is upward reaction, because it is downward force at its this end support. Therefore left is upward, same W, and right down, left up, right down, it is simply positive shear force diagram, and it should be uniform one. Okay, so then how can we find the reaction forces? So before that, before the beam analyzing or any beam, if you want to find the shear force and bending moment on this beams, we must find the reaction forces. So by knowing the reaction forces only, then we can calculate the shear forces and bending moment along the spans of the beam. Based on the support condition of the beam, first we have to arrive the how many number of total reactive forces. In case of simply supported beam, it has only two reactive forces. One is the reaction, upward reaction at support A, another one is the upward reaction at support B. Like that, these two reactive forces will be calculated using two static equilibrium equations such as sigma m equal to 0 and sigma v equal to 0. So these two are nothing but the static equilibrium equations. The use of these two equations, we can find the or we can calculate the reactive forces or reactions on these two supports. So so for that we have to formulate the equilibrium equation. In order to formulate these equilibrium equations, we should also use the sign convention, in which all clockwise moments, let it be positive or negative, whatever may be. Like that, if we put the if we give the positive sign for all clockwise moment, then we can use the counterclockwise moments as negative. Otherwise, if we put the negative sign for clockwise moments, then we can use the positive sign for counterclockwise moments, like that. Then finally we can use sum of clockwise moments should be equal to sum of counterclockwise moments, and therefore we can get this equation sigma m equal to 0. Similarly, while using sigma v equal to 0, equations for calculating the reactive forces. Okay, so these two equations major are these two main static equilibrium equations are using for calculating the reactive forces on given beams, either simply supported beam or cantilever beam. So let us have, with the use of these all sign conventions, now we try to solve this problem. Here you see that a simply supported beam of span 6 meter carries loads of 30 kilonewton and 24 kilonewton at a distance of 2 meter and 3 meter from the left end. Now compute the reactions and draw the SFD. So you see that there is a simply supported beam and it is subjecting a two concentrated forces 30 kilonewton, which is acting 2 meter from the left support, and another concentrated force 24 kilonewton, which is acting 3 meter from the left support at point D. Now let us try to draw the SFD for this case. In this case, first we must find the reactive forces at A and B, that is reactive forces at A, let it be RA, and the reactive forces at support B, let it be RB. We must find this RA and RB. For that, we must use the equilibrium equation, that is sigma m equal to 0. What is meant by sigma m equal to 0? That is, we just make the moments at any point. We just find the moments, sum of moments at any point. Sigma m means the sum of moments at any point should be equal to 0. Suppose I took this point, sigma m equal to 0. I can write the equilibrium equation sigma m equal to 0, and also I can use the sigma m equal to 0 equation at also support B. So like that, I use the sigma m at support B equal to 0, and therefore I take the I write the equation RA into distance x meter. I just put this sign plus because here I use the positive sign for reactive forces as clockwise moments, that is RA into 6, which induces a clockwise moment into 6 minus 24 into 3, because it is 3 meter, the remaining distance is 3 meter, and it is inducing the anti-clockwise moment, therefore I put this sign minus, and 30 into 4, it is also minus because it induces anti-clockwise moments. So these sign convention should be used only for writing the equilibrium equations, not for bending moment. Bending moment, there is another sign convention, that is all sagging moments are positive and all hogging moments are negative. The sagging moments are developed due to the reactive forces, upward force into distance. The hogging moment is produced due to the downward forces acting on the beam into distance, which inducing the hogging moment. Okay, that things are to be used in the calculation of bending moment at the differences. But here we are writing the equilibrium equation in order to find the reactive forces RA, because there are two unknowns RA and RB. To solve these two unknowns, we need two more equilibrium equations. So in which here we use one equilibrium equation, that is sigma mb at point B equal to 0. So for that I just write the equilibrium equations RA into 6 minus 24 into 3 minus 30 into 4 is equal to 0. We can also write the equilibrium equation at any point. Sigma m at this point equal to 0, this point is equal to 0, this point. But why do I write particularly at sigma m equal to 0? So that I can find RA with this one equation. Otherwise I suppose I choose the point at D, sigma md equal to 0. So that I can write the equation RA into 3 minus 30 into 1. Then again minus RB into this distance 3. So I have two unknowns in this single equations. Then one more equations I can write sigma v equal to 0, in which there are two unknowns RA and RB. Now both equations can be solved simultaneously, and I can find two unknowns RA and RB. Like that we can solve. So but if I write the sigma m equal to 0 equation at B, so that from that one equation I can find the one reactive forces. So that's why I write the sigma mb equal to 0, or we can write the equation sigma ma equal to 0, from which we can find the RB. So in that equation there is only one unknown RB we can find. Okay. Then once if you know the RA or RB, the right of this equilibrium equation, for this case we can find the RA. The RB can be calculated the total force acting on the beam minus the RA, so that we can find RB. So because whatever the loads acting on this beam, that two loads are shared by these two supports. Okay. So once if we know the load shared by support B or A, let it be RA is equal to 32, the total load is 54, the remaining loads must be shared by only the support B. So 54 minus 32, that is 22 kilonewton, is nothing but the reactive forces at support B. So like that we can find. So once if we know these two reactive forces, then we can start to find the shear force and bending moment at every sections. Okay, so here I want to know the shear force at C. Shear force at CD is nothing, this thing can be calculated. We just make the algebraic sum, either left side of this C or right side of this C. Suppose I just take the left side of this C, there is only one upward reactive forces, so it is acting left side of this C, and this reactive force is acting upward direction, therefore left up it is always positive, and therefore 32 is positive. In between A and C there is no forces, and therefore it comes horizontal line. At C there is downward 30. Okay, so this is left up, at C down 30, but totally it is 32. Now it is getting down only 30. The remaining 2 again goes flat because there is no force in between C and D. At D it gets down 24. So here 2 minus 24, it is 22. Okay, with respect to D, at D we have, what is the shear force? We can find at D. So I just make the right side force. There is only right up is negative 22. So at D it is having only the 22 kilonewton negative. Am I correct? This is negative 22 kilonewton at D. Okay. Yes. Otherwise you just make, you must check this side. At D, just make the algebraic sum with respect to this left side, left two portions. There is upward plus 32, then left to down. C is with respect to the support D. At C there is F downward force, it is left to down. With respect to this D, it is left side. So this is 30. So 32 minus 30, what is? It is 2. Okay, 2 is positive. So that positive 2 is getting at upward, and a negative 22 is getting at downward. So like that we have shear force at this section. At the end of B, at support B, there is an upward 22. Okay, upward 22, it is 22 kilonewton. So like that we can draw the SFD for this given problem. So let us have an overhanging beam. In this beam we can also find the reaction forces, and we can also find the SFD. So as usual, we just, in order to find the reactive forces, taking the moments about at A, sigma MA equal to 0. For that I can write the equation RB into 3. Let it be anti-clockwise. I just put the sign plus for anti-clockwise moments, therefore plus, and all clockwise moments just I put the sign negative, therefore minus 9 into 4. This is the forces of, total forces of this UDL, uniform distributed load, and this load is assumed as acting at centroid of this span of the load. Therefore total length of the load is 4 meter, and therefore this UDL is acting as concentrated force as 36 kilonewton at centroid of this load span. So from A it is about 2 meter, and therefore it is clockwise. We just put the minus sign for writing this equilibrium equation. So 36 into 2, I just write like that. So 9 into 4 is nothing but, we just convert this UDL into concentrated force. That concentrated force is acting at a centroid of this loading span. So the total span of the load UDL is 4 meter, therefore it is acting at 2 meter from the support A. Now we just take the sum of moments at A equal to 0. So we are taking the, or we are writing the moment equation with respect to A, and therefore this 9 into 4, 36 kilonewton at the center here, and it, with respect to this A, it is acting clockwise, and therefore I put the sign minus. 9 into 4 is concentrated force, it is acting at 2 meter from the left support, therefore into 4 by 2. So now we obtain the RB is equal to 24 kilonewton. Therefore RA is equal to, so whatever the force acting on this beam, it must be shared by these two supports A and B. So now the total forces is 9 into 4, 36. Now RB is 24, therefore RA should be 12. So the beam carries a uniformly distributed UDL, hence the shear force will change uniformly from A to B and from B to C. So the shear force also uniformly varying. Okay, so because it is UDL, so shear force at A, RA is equal to plus 12. Upward it is having RA is equal to, so because it is A is a left support at any section, A is a left support, it is upward, left up is positive, that is RA is equal to 12. Then A to B, it is uniformly distributed, the load is varying, it is 12 upward, whereas the downward forces, it is uniformly distributed, and therefore the distance between A to B is 3 meter. Now A to B, there is 9 into 3, 27 kilonewton is getting down, and therefore here upward 12 and downward is when it meets at a point 0. Again, in order to the total force down from here A to B is 27, and therefore further it moves 15 towards negative side. Therefore now we get the total downward forces 27 kilonewton from A to B. Okay, at B there is an upward force of how much? It has been calculated as 24 kilonewton. Therefore there will be an upward positive 9 because 15 and a 9 upward forces. Then again the load is varying up to C. Its span is 1 meter and that is 9. So the 9 comes down to C and meets at 0 at C. So like that we can draw the SFT for this overhanging beam. So over AB, the shear force will change uniformly as a straight line from plus 12 to minus 15, the change being 27, the value of the load between A and B. Yes, the shear force to the right be RA minus 9 into 3 plus RB at B. So, and for here for a section to the right of B, RB is up and hence it is positive. Shear force at B, 12 minus 24 plus 27 plus 24, it should be 9. So that value becomes 9. Okay, at B. So like that we can find the shear force at all sections. So next let us see the bending moment diagram, BMD. Okay, the bending moment at any section is the difference of moments due to the upward reactive forces, that is sagging moment about that section, and downward forces, hogging moment about that section. So bending moment is nothing but the net bending moment. It can be calculated as the net moments at any section. Suppose I want to know the bending moment at any section, it is nothing but the net moments of at that section. Okay, the net moment is being calculated as the difference of sagging bending moment, and hogging moment with respect to that section. That's all. So let us have this problem. You see that as usual, first we must find the RE and RB, for which we just write the equilibrium equation sigma mb equal to 0. Therefore RA into these are all clockwise. I just put the positive sign for clockwise moments and anti-clockwise moments for negative, so that I just form the equation like this. Therefore I get the RA is equal to 32 kilonewton and therefore RB is equal to 22 kilonewton. Now I can draw the BMD like this. Suppose what is the value of bending moment at A? It should be 0 because at support A it allows rotation. If there is any resistance against rotation or moment, there will be a reactive moment at support. But in case of hinged support or simply support at A, it doesn't have any reactive moment, and therefore because it allows rotation, full rotation, and therefore moment at A should be equal to 0. So this is the baseline for the bending moment diagram. At A it should be 0. At C there is only the positive moment. I just find the bending moment at C by making algebraic sum through all moments on left side. Therefore there is only one moment, 32 into 2. It is upward force into 2, reactive force. It is producing sagging positive, 32 into 2, 64 kilonewton meter. Or you can also check from right side, just make the algebraic sum of moments. This is the reactive force 22 kilonewton into 4. I think it is 4 with respect to C. So 22 into 4, it is 88 kilonewton meter. So it is nothing but reactive forces, moment due to reactive forces. It is sagging, therefore positive. Then 24 into 1, it is nothing but the applied forces into distance which produces the hogging. Therefore it is minus 24 into 1. So 88 minus 24, which or sorry, 88 minus 24, finally we have 64 kilonewton meter. The net moment is sagging. So like that here. And also I can also find the bending moment at dt. It is also RB into this distance, that is 22 into 3, it is 66 kilonewton meter. And at support B it is 0. The bending moment value is 0 because it allows rotation. There is no any reactive moment produced. So like that, now I can connect these all points by straight line. Why do I connect the all points as straight line? Because for this case I can write the equation. So RA into, let it be a distance x with in between A and C. Why do we connect by straight line? The moment equation becomes, suppose let the distance of I just choose this section here, the less distance from A, it will be x. Therefore RA into x. RA into x means it is nothing but the equation for straight line or linear line. So and therefore I connect this one straight line. Like that, C in between C and D you can also form the equation RA into the distance x and 30 into the distance may be 2 plus x minus 2. Okay, x minus 2. So when we when we resolve this equation, again it comes a straight line. Therefore I just connect the straight line. Then in between these two it is also a straight line equation. So we just connect all these points through the line. Okay, so and therefore this is the bending moment diagram or bending moment diagram shape, the shape of the bending moment diagram for this particular case. So this is the another problem. We can find the shear force as well as bending moment. So like that we can solve the different. This is the shape of the shear force diagram for this case. Since it is subjected UDL, the shear force becomes the linearly varying, and in between this it becomes like this. The shape becomes like this. And now this is the diagram of the SFD shear force diagram, and since it is subjected by UDL, the points which connects in between, that is moment points between this A and C, it should be connected by the parabolic curve, because once you form the equation with respect to this point, you just write the equation bending moment RA into this distance x minus W into x, this UDL, and it should be acting at center of this x by 2. Therefore W into x by 2, so it is Wx squared by 2. Now it becomes the second order parabola curve, and therefore it is second degree curve of parabola in this region, this UDL region. So like that the equation forms. Okay, this is another problem that we can see. So like that we can solve the different problems in this case, and we can draw the SFD and BMD, the use of same sign conventions and same method. So with this I just conclude the SFD and BMD. How can we draw the shear force diagram and bending moment diagram for the different types of beams and for different cases of loads. So thank you.